Welcome to this lecture in the ongoing series of lectures in real analysis. Today we will be looking at integration by parts and change of variables. Today will be a very short lecture. Let us look at what we have done so far and the things that we need for today's material. So one thing that I want to introduce is this notational convention, which I somehow forgot to introduce earlier, but doesn't matter. So suppose you have an integrable function, and of course by integrable I mean Riemann integrable. Then we write this, where you see b is greater than a, but we are writing b below and a above. So we write this to mean that. Okay, and now let us recall the fundamental theorem of calculus. So we have some continuous function, and we define another function out of it by, let's say, this recipe. Then we showed that this function f is differentiable, and in fact its derivative is same as the function little f, right? And then we showed something more. We showed that if you have some function capital G which is differentiable and which has the property that its derivative is same as f, then the function looks like this. So essentially this is the only function which satisfies this condition. I say essentially because there is a little bit of a room of choosing this constant to be whatever you want. We could have very well taken fx as this plus whatever constant we want, and it wouldn't change a thing because the derivative of constant is 0. Anyway, so this is what we call the fundamental theorem of algebra, or what am I saying, fundamental theorem of calculus. And one of the consequences of it was that suppose you start with a continuously differentiable function, meaning a function whose derivative is continuous, then if you integrate the derivative, you get the difference between the values at the end point of the domain. And we said that this is basically like saying that if you sum up all the local changes, you get the global change. So that is basically what this is saying. All right. And let us recall the chain rule because we need it today. So we have some differentiable function, and let's say its image is I. And since differentiable functions are continuous, the I, meaning the image of phi, is also an interval. In fact, it is going to be a closed interval. A continuous image of a closed interval is again a closed interval. So fine, so we have now some other differentiable function defined on I, where I is the image of phi. Then the claim of the chain rule is that this composite, which makes sense because I is the image of phi, so this composite makes sense. Then this composite is also differentiable, and its derivative is given by this recipe. So you have this function, and then you multiply that function by phi prime. So this is a pointwise product. So that was the chain rule. All right. So now for the problems. There are 3 problems here. I guess maybe I should have given this much earlier. This problem somehow I kind of did not include it earlier, but anyway, one can solve it now. Yeah, this is also something very interesting that now we can integrate surds also given what we have done. So fine. All right, so let us quickly finish this lecture. So yeah, so what we have is 2 functions which are continuously differentiable. So C1 functions means continuously differentiable function. Let me just write continuously differentiable. Be continuously differentiable. So then the claim is that if you integrate this funny looking thing, you get that funny looking thing. So why is this useful? Well, if you ever integrated things in your high school where you have some product of, you have some crazy integral, but then you recognize it as, in this fashion, then it can help sometimes. Maybe this is easier to integrate than that. So this is why it can help. But my reason for introducing this is that first of all, it should be introduced in any real analysis course, and second is that I need this theorem for my next application, in the next lecture, which is on Taylor's theorem. So despite doesn't, it's apparent lack of usefulness, because what the hell are you going to do with this formula? It is definitely of theoretical importance, and we'll see this in Taylor's theorem. Anyway, so let me give a proof as to why this is true. So the whole point is this. So we know that f times g is also continuously differentiable, because product of two continuously differentiable functions is continuously differentiable. Therefore, by therefore by the fundamental theorem of calculus, we have, if you integrate this from a to b, you get this value at b minus this value at a, which is same as saying, now here we apply the product rule of differentiation. So this is f prime g plus, let me write a plus here, plus a to b f g prime, and the thing on the right side is of course f b g b, because that's what it means to evaluate the product of two functions at a point. We have that, and if you rearrange this, you get that. If you just rearrange the things, you get that. So as simple as that. It's just product rule and fundamental theorem of calculus. Okay. And now integration by substitution or change of variables formula. So here what we have is a continuously differentiable function, and let's say I is the image of that function. So then what we have is some function defined on the image of phi. So let f be a continuous function. I think it is enough to just assume integrability of f, but let me do it for continuous functions. So let f be a continuous function. Then, so before I make the statement, again, note that this is a closed interval. Continuous image of any closed interval is a closed interval. So I is a closed interval, and the claim is that if you integrate this, again, a little bit funny looking thing, then you get and here it is completely possible that phi a is greater than phi b. So this is the we introduced a convention at the beginning, so you use that convention here. Alright, it is also possible that phi a equals phi b, in which case this is 0. So here what we have is the pointwise product of this function with that function. Okay, so let's prove this. So here is the proof. So we define capital F, very bad handwriting, define capital F as phi a to x for all x in the interval I. So by fundamental theorem of calculus, or whatever we did the last time, we know the derivative of f is at any point x is nothing but f of x. This is for all x in I. And now by chain rule, we have that f composite phi product with phi prime is, well, this is not chain rule, this is just tautology, but this is chain rule. Okay, so we have used chain rule to deduce that, and therefore this integral from a to b is the integral a to b of this function, which by a fundamental theorem of calculus is that. Which is by definition of capital F, or rather, okay, let me write one more step. By definition of capital F, this is phi a to phi b integral of f minus phi a to phi a integral of f. But the second one is of course 0, so this is nothing but phi a to phi b integral of f. And that proves our claim. So here we use the fundamental theorem of calculus, or maybe a consequence of it. Maybe, I don't know if I called it the fundamental theorem of calculus, but a consequence of the fundamental theorem of calculus. Okay, so we have that, and now let us see a very silly application of it, because so far we do not have a big repertoire of functions which we can differentiate or integrate. All we have basically are polynomials and surds, and inverses of differentiable functions are differentiable. That much we know. And what are differentiable functions? Polynomials. So we don't have too many. And we also have some algebra of differentiable functions. So if you invert a differentiable function, you again get a differentiable function, but still we do not have a very rich collection of things which we can differentiate or integrate. So all I can give is a silly example. But hopefully it will illustrate how to use this theorem, change of variables. So suppose I'm interested in evaluating this. This is an integral at which I want to evaluate, and of course this is a polynomial, so I already know how to calculate it. But the point I want to get across is one can do it this way. So we introduce a half and we write it in this fashion. Okay, so I claim that this is equal to half of integral of 0 to 4 x plus 1 dx. So why is that? I want to explain this, what happened here. So what happened is that you have your function phi, which takes 0, 2 to, of course, 0, 4, and the function is x going to x square, this function. And then I have this function f. So I am defining these functions, it's up to me. I'm defining phi, I'm defining f, and f is defined by the recipe. It takes little x to x plus 1. So this is the composition of these two would become x going to x square plus 1, and this is your f composed with phi. Right? Let me make it a little bit more beautiful. Yeah, so we have that, and therefore this integral 0 to 2, or rather half of x square plus 1 2x dx, this is nothing but half of 0 to 2 f composed phi prime. That's it. That's what that is. And now if we apply the change of variables, we get half of phi 0 to phi 2, and here we'll have f, which is by definition of phi, this is 0 to 4 f. And what is f? f is x plus 1. So that's what is happening. Okay, I think this is all that I wanted to say. Yeah, this is all. As usual, like, comment, share, subscribe. Thank you for listening, and I'll see you next time.